The Serial Peripheral Interface or SPI bus is a synchronous serial data link, a de facto standard, named by Motorola, that operates in full duplex mode. It is used for short-distance, single-master communication, for example in embedded systems, sensors, and SD cards. Devices communicate in master-slave mode where the master device initiates the data frame. Multiple slave devices are allowed with individual slave select lines. Sometimes SPI is called a 4-wire serial bus, contrasting with 3, 2, and 1-wire serial buses. SPI is often referred to as SSI. Interface. The MOSI-MISO convention requires that, on devices using the alternate names, SDI on the master be connected to SDO on the slave, and vice versa. Chip select polarity is rarely active high, although some notations suggest otherwise. Slave select is used instead of an addressing concept. Operation. The SPI bus can operate with a single master device and with one or more slave devices. If a single slave device is used, the SS pin may be fixed to logic low if the slave permits it. Some slaves require a falling edge of the chip select signal to initiate an action. An example is the Maximax 1242 ADC, which starts conversion on a higher low transition. With multiple slave devices, an independent SS signal is required from the master for each slave device. Most slave devices have tri-state outputs, so their MISO signal becomes high impedance when the device is not selected. Devices without tri-state outputs cannot share SPI bus segments with other devices. Only one such slave could talk to the master, and only its chip select could be activated. Data transmission. To begin a communication, the bus master first configures the clock, using a frequency less than or equal to the maximum frequency the slave device supports. Such frequencies are typically up to a few megahertz. The master then transmits the logic 0 for the desired chip over the chip select line. A logic 0 is transmitted because the chip select line is active low, meaning its off state is a logic 1. On is asserted with a logic 0. If a waiting period is required, then the master must wait for at least that period of time before starting to issue clock cycles. During each SPI clock cycle, a full duplex data transmission occurs. The master sends a bit on the MOSI line. The slave reads it from that same line. The slave sends a bit on the MISO line. The master reads it from that same line. Not all transmissions require all four of these operations to be meaningful, but they do happen. Transmissions normally involve two shift registers of some given word size, such as 8 bits, one in the master and one in the slave. They are connected in a ring. Data is usually shifted out with the most significant bit first, while shifting a new least significant bit into the same register. After that register has been shifted out, the master and slave have exchanged register values. Then each device takes that value and does something with it, such as writing it to memory. If there is more data to exchange, the shift registers are loaded with new data and the process repeats. Transmissions may involve any number of clock cycles. When there is no more data to be transmitted, the master stops toggling its clock. Normally, it then deselects the slave. Transmissions often consist of 8-bit words. A master can initiate multiple such transmissions if it needs. However, other word sizes are also common, such as 16-bit words for touchscreen controllers or audio codecs, like the TSC2101 from Texas Instruments. Or 12-bit words for many digital to analog or analog to digital converters. Every slave on the bus that has not been activated using its chip select line must disregard the input clock and MOSI signals, and must not drive MISO. The master must select only one slave at a time. Clock polarity and phase. In addition to setting the clock frequency, the master must also configure the clock polarity and phase with respect to the data. Freescale's SPI block guide names these two options as CPOL and CPHA respectively, and most vendors have adopted that convention. The timing diagram is shown to the right. The timing is further described below and applies to both the master and the slave device. At CPOL equals 0 the base value of the clock is 0, for CPHA equals 0, data are captured on the clock's rising edge and data is propagated on a falling edge. For CPHA equals 1, data are captured on the clock's falling edge and data is propagated on a rising edge. At CPOL equals 1 the base value of the clock is 1, for CPHA equals 0, data are captured on clock's falling edge and data is propagated on a rising edge. For CPHA equals 1, data are captured on clock's rising edge and data is propagated on a falling edge. That is, CPHA equals 0 means sample on the leading clock edge, while CPHA equals 1 means sample on the trailing clock edge, regardless of whether that clock edge is rising or falling. Note that with CPHA equals 0, the data must be stable for a half cycle before the first clock cycle. The MOSI and MESO signals are usually stable for the half cycle until the next clock transition. SPI master and slave devices may well sample data at different points in that half cycle. This adds more flexibility to the communication channel between the master and slave. Some products use different naming conventions. For example, the TIMSP430 uses the name UCCKPL instead of CPOL, and its UCCKPH is the inverse of CPHA. When connecting two chips together, the clock phase initialization values must be examined to be sure of using the right settings. Mode numbers. The combinations of polarity and phases are often referred to as modes, which are commonly numbered according to the following convention, with CPOL as the high-order bit and CPHA as the low-order bit. For microchip PIC/ATMELAVIA/ARM-based microcontrollers, for other microcontrollers, another commonly used notation represents the mode as a tuple. For example, the value 0, 1, would indicate CPOL equals 0 and CPHA equals 1, refer to section Serial Peripheral Interface in your microdata sheet controller for more information. Independent slave SPI configuration. In the independent slave configuration, there is an independent chip select line for each slave. This is the way SPI is normally used. Since the MESO pins of the slaves are connected together, they are required to be tri-state pins. Daisy chain SPI configuration. Some products with SPI bus are designed to be capable of being connected in a daisy chain configuration, the first slave output being connected to the second slave input, etc. The SPI port of each slave is designed to send out during the second group of clock pulses an exact copy of what it received during the first group of clock pulses. The whole chain acts as an SPI communication shift register. Daisy chaining is often done with shift registers to provide a bank of inputs or outputs through SPI. Such a feature only requires a single SS line from the master, rather than a separate SS line for each slave. Applications that require a daisy chain configuration include SGPIO and JTAG. Valid SPI communications. Some slave devices are designed to ignore any SPI communications in which the number of clock pulses is greater than specified. Others do not care, ignoring extra inputs and continuing to shift the same output bit. It is common for different devices to use SPI communications with different lengths, as, for example, when SPI is used to access the scan chain of a digital IC by issuing a command word of one size and then getting a response of a different size. Interrupts. SPI devices sometimes use another signal line to send an interrupt signal to a host CPU. Examples include pen-down interrupts from touchscreen sensors, thermal limit alerts from temperature sensors, alarms issued by real-time clock chips, SDIO, and headset jack insertions from the sound codec in a cell phone. Interrupts are not covered by the SPI standard. Their usage is neither forbidden nor specified by the standard. Example of bit banging the SPI master protocol. Below is an example of bit banging the SPI protocol as an SPI master with CPOL equals 0, CPHA equals 0, and 8 bits per transfer. The example is written in the C programming language. Because this is CPOL equals 0, the clock must be pulled low before the chip select is activated. The chip select line must be activated, which normally means being toggled low, for the peripheral before the start of the transfer, and then deactivated afterwards. Most peripherals allow or require several transfers while the select line is low. This routine might be called several times before deselecting the chip. Pros and cons of SPI. Advantages: full duplex communication in the default version of this protocol. Higher throughput than ES2C or SMBUS, complete protocol flexibility for the bits transferred, not limited to 8-bit words, arbitrary choice of message size, content, and purpose. Extremely simple hardware interfacing, typically lower power requirements than ES2C or SMBUS due to less circuitry, no arbitration or associated failure modes. Slaves use the master's clock, and do not need precision oscillators. Slaves do not need a unique address. Unlike ES2C or GPIB or SCSI, transceivers are not needed. Uses only 4 pins on IC packages, and wires in board layouts or connectors, much fewer than parallel interfaces, at most one unique bus signal per device. All others are shared. Signals are unidirectional, allowing for easy galvanic isolation, not limited to any maximum clock speed, enabling potentially high throughput. Disadvantages: requires more pins on IC packages than ES2C, even in the 3-wire variant, no in-band addressing. Out-of-band chip select signals are required on shared buses, no hardware flow control by the slave, no hardware slave acknowledgement, supports only one master device, no error checking protocol is defined, without a formal standard, validating conformance is not possible, only handles short distances compared to RS-232, RS-485, or CAN bus, many existing variations, making it difficult to find development tools like host adapters that support those variations. SPI does not support hot plugging. Interrupts must be either be implemented with out-of-band signals or be faked by using periodic polling similarly to USB 1.1 and 2.0. Some variants like multi-IO SPI and 3-wire serial buses defined below are half-duplex. Applications: the board real estate savings compared to a parallel I/O bus are significant, and have earned SPI a solid role in embedded systems. That is true for most system-on-a-chip processors, both with higher-end 32-bit processors such as those using ARM, MIPS, or PowerPC, and with other microcontrollers such as the AVR, PIC, and MSP430. These chips usually include SPI controllers capable of running in either master or slave mode. In-system programmable AVR controllers can be programmed using an SPI interface. Chip or FPGA-based designs sometimes use SPI to communicate between internal components. On-chip real estate can be as costly as its on-board cousin. The full duplex capability makes SPI very simple and efficient for single-master single-slave applications. Some devices use the full duplex mode to implement an efficient, swift data stream for applications such as digital audio, digital signal processing, or telecommunications channels, but most off-the-shelf chips stick to half-duplex request-response protocols. SPI is used to talk to a variety of peripherals, such as sensors, temperature, pressure, ADC, touch screens, video game controllers, control devices, audio codecs, digital potentiometers, DAC, camera lenses, Canon EF lens mount, communications, Ethernet, USB, USART, CAN, IEEE 800 2.15.4, IEEE 800 2.11, handheld video games, memory, flash and EEPROM, real-time clocks, LCD, sometimes even for managing image data, any MMC or SD card. For high-performance systems, FPGAs sometimes use SPI to interface as a slave to a host, as a master to sensors, or for flash memory. Used to bootstrap if they are SRAM based. JTAG is essentially an application stack for a 3-wire SPI flavor, using different signal names, TCK not SCK, TDI not MOSI, TDO not MISO. It defines a state machine, protocol messages, a core command set, the ability to daisy chain devices in a scan chain, and how vendors define new commands. The devices in a scan chain are initially treated as a single device, and transitions on TMS update their state machines. Once the individual devices are identified, commands may be issued that affect only one device in that scan chain. Different vendors use different JTAG connectors. Bit strings used in JTAG are often long and not multiples of 8-bit words. For example, a boundary scan reports signal state on each of several hundred pins. SGPIO is essentially another application stack for SPI designed for particular backplane management activities. SGPIO uses 3-bit messages. Standards: the SPI bus is a de facto standard. However, the lack of a formal standard is reflected in a wide variety of protocol options. Different word sizes are common. Every device defines its own protocol, including whether or not it supports commands at all. Some devices are transmit-only. Others are receive-only. Chip selects are sometimes active-high rather than active-low. Some protocols send the least significant bit first. Some devices even have minor variances from the CPOL-CPHA modes described above. Sending data from slave to master may use the opposite clock edge as master to slave. Devices often require extra clock idle time before the first clock or after the last one, or between a command and its response. Some devices have 2 clocks, one to read data, and another to transmit it into the device. Many of the read clocks run from the chip select line. Some devices require an additional flow control signal from slave to master, indicating when data are ready. This leads to a 5-wire protocol instead of the usual 4. Such a ready or enable signal is often active-low, and needs to be enabled at key points such as after commands or between words. Without such a signal, data transfer rates may need to be slowed down significantly, or protocols may need to have dummy bytes inserted, to accommodate the worst case for the slave response time. Examples include initiating an ADC conversion, addressing the right page of flash memory, and processing enough of a command that device firmware can load the first word of the response. Many SPI chips only support messages that are multiples of 8 bits. Such chips cannot interoperate with the JTAG or SGPIO protocols, or any other protocol that requires messages that are not multiples of 8 bits. There are also hardware-level differences. Some chips combine MOSI and MISO into a single data line. This is sometimes called 3-wire signaling. Another variation of SPI removes the chip select line, managing protocol state machine entry-exit using other methods. This is not usually called 3-wire though. Anyone needing an external connector for SPI defines their own, UEXT, JTAG connector, secure digital card socket, etc. Signal levels depend entirely on the chips involved. Development tools: when developing or troubleshooting systems using SPI, visibility at the level of hardware signals can be important. Host adapters: there are a number of USB hardware solutions to provide computers, running Linux, Mac, or Windows, SPI master and/or slave capabilities. Many of them also provide scripting and/or programming capabilities. An SPI host adapter lets the user play the role of a master on an SPI bus directly from PC. They are used for embedded systems, chips and peripheral testing, programming and debugging. The key parameters of SPI adapters are the maximum supported frequency for the serial interface, command-to-command latency and the maximum length for SPI commands. It is possible to find SPI adapters on the market today that support up to 100 MHz serial interfaces, with virtually unlimited access length. SPI protocol being a de facto standard, some SPI host adapters also have the ability of supporting other protocols beyond the traditional 4 wires SPI. Examples of SPI adapters: protocol analyzers. SPI protocol analyzers are tools which sample an SPI bus and decode the electrical signals to provide a higher-level view of the data being transmitted on a specific bus. Oscilloscopes: every major oscilloscope vendor offers oscilloscope-based triggering and protocol decoding for SPI. Most support 2, 3, and 4-wire SPI. the triggering and decoding capability is typically offered as an optional extra. SPI signals can be accessed via analog oscilloscope channels or with digital MSO channels. Logic analyzers, when developing and/or troubleshooting the SPI bus, examination of hardware signals can be very important. Logic analyzers are tools which collect, analyze, decode, store signals so people can view the high-speed waveforms at their leisure. Logic analyzers display timestamps of each signal level change, which can help find protocol problems. Most logic analyzers have the capability to decode bus signals into high-level protocol data and show ASCII data. Related terms, intelligent SPI controllers, the queued serial peripheral interface is one type of SPI controller, not another bus type. It uses a data queue with programmable queue pointers allowing some data transfers without CPU intervention. It also has a wraparound mode allowing continuous transfers to and from the queue with no CPU intervention. Consequently, the peripherals appear to the CPU as memory-mapped parallel devices. This feature is useful in applications such as control of an AD converter. Other programmable features include SPI are chip selects and transfer length delay. SPI controllers from different vendors support different feature sets. Such DMA queues are not uncommon, although they may be associated with separate DMA engines rather than the SPI controller itself, such as used by multi-channel buffered serial port. Most SPI master controllers integrate support for up to 4 chip selects, although some require chip selects to be managed separately through GPIO lines. Microwire, often spelled I1/4 wire, is essentially a predecessor of SPI and a trademark of National Semiconductor. It's a strict subset of SPI, half-duplex, and using SPI mode 0. Microwire chips tend to need slower clock rates than newer SPI versions. Perhaps 2 MHz versus 20 MHz. Some microwire chips also support a 3-wire mode, which fits neatly with the restriction to half-duplex. Microwire Plus is an enhancement of microwire and features full duplex communication and support for SPI mode 0 and 1. There was no specified improvement in serial clock speed. 3-wire serial buses, as mentioned, one variant of SPI uses single bidirectional data line instead of 2 unidirectional ones. This variant is restricted to a half-duplex mode. It tends to be used for lower performance parts, such as small EEPROMs used only during system startup and certain sensors, and microwire. Few SPI master controllers support this mode, although it can often be easily bit-banged in software. Multi-IO SPI, as opposed to 3-wire serial buses, multi-IO SPI uses multiple parallel data lines to increase throughput. Dual I/O SPI using 2 data lines has comparable throughput to fast single I/O. Quad I/O SPI using 4 data lines has approximately double the throughput. Multi-IO SPI devices tend to be half-duplex similar to 3-wire devices to avoid adding too many pins. These serial memory devices combine the advantage of more speed with reduced pin counters compared to parallel memory. MSPI is a modification initially developed by Demitec for their programmable modules. Unlike the standard SPI, 4 signal lines are always required no matter of the number of slave devices. Its overall simplicity allows the use of standard SPI controllers with a very thin software layer. All slave devices share the same SS line, along with the other 3 SPI signals, SCLK, MOSI and MISO. Additionally, all slave devices normally have their MISO line disconnected from the bus in a high impedance state. As in the standard SPI, begin of transmission is marked by the activation of the SS line low and the end is marked by its return to high. MSPI requires the bus master to issue a slave address as mandatory first word in every transmission. Since all slave devices share the same SS line, the address word will be received by all of them at the same time. From that point further, only the device with the specified address will connect its MISO line to the bus and start communicating, while all other slave devices will ignore any data and wait for a new start of transmission and address. MSPI solves some of the basic disadvantages of the standard SPI at the expense of a slight decrease in the overall communication speed due to the initial addressing. Intel Enhanced Serial Peripheral Interface Bus. Intel is currently developing a successor to its low pin count bus that it calls the Enhanced Serial Peripheral Interface Bus, or ESPI for short. Intel aims to allow the reduction in the number of pins required on motherboards compared to systems using LPC, have more available throughput than LPC, reduce the working voltage to 1.8 volts to facilitate smaller chip manufacturing processes, allow ESPI peripherals to share SPI flash devices with the host, tunnel previous out-of-band pins through the ESPI bus, and allow system designers to trade off cost and performance. The ESPI bus can either be shared with SPI devices to save pins or be separate from the SPI bus to allow more performance, especially when ESPI devices need to use SPI flash devices. This proposed standard defines an alert signal that is used by an ESPI slave to request service from the master. In a performance-oriented design or a design with only one ESPI slave, each ESPI slave will have its alert pin connected to an alert pin on the ESPI master that is dedicated to each slave, allowing the ESPI master to grant low-latency service because the ESPI master will know which ESPI slave needs service and will not need to poll all of the slaves to determine which device needs service. In a budget design with more than one ESPI slave, all of the alert pins of the slaves are connected to one alert pin on the ESPI master in a wired OR connection, which will require the master to poll all the slaves to determine which ones need service when the alert signal is pulled low by one or more peripherals that need service. Only after all of the devices are serviced will the alert signal be pulled high due to none of the ESPI slaves needing service and therefore pulling the alert signal low. This proposed standard allows designers to use 1-bit, 2-bit, or 4-bit communications at speeds from 20 to 66 MHz to further allow designers to trade off performance and cost. All communications that were out of band of the LPC bus like general purpose input-output and system management bus are tunneled through the ESPI bus via virtual wire cycles and out-of-band message cycles respectively in order to remove those pins from motherboard designs using ESPI. This proposed standard will support standard memory cycles with lengths of 1 byte to 4 KB of data, short memory cycles with lengths of 1, 2, or 4 bytes that have much less overhead compared to standard memory cycles, and I/O cycles with lengths of 1, 2, or 4 bytes of data which are low overhead as well. This significantly reduces overhead compared to the LPC bus, whose throughput is nearly totally dominated by overhead. The standard memory cycle allows a length of anywhere from 1 byte to 4 KB in order to allow its overhead to be amortized over a large transaction. ESPI slaves are allowed to initiate bus master versions of all of the memory cycles. Bus master I/O cycles, which were introduced by the LPC bus specification, and ISA-style DMA including the 32-bit variant introduced by the LPC bus specification, are not present in ESPI. Therefore, bus master memory cycles are the only allowed DMA in this standard. ESPI slaves are allowed to use the ESPI master as a proxy to perform flash operations on a standard SPI flash memory slave on behalf of the requesting ESPI slave. 64-bit memory addressing is also added, but is only permitted when there is no equivalent 32-bit address. See also: related buses, list of network buses. Related connectors, secure digital, SD, SDHC, SDXC cards. UEXT connector. Universal metering interface, references. External links, Intel ESPI, Introduction to SPI and I2C protocols, serial buses information page, SPI introduction with helpful diagrams, serial flash. Lots of good information on SPI part manufacturers and models. SPI, PIC Micro Serial Peripheral Interface, microchip tutorial on SPI. OpenCore's open source implementation of SPI written in Verilog. Simpler MC68HC11 version, SPI flash memory controller, HDL design house, SPI bus tutorial, MSPI description.